Okay, this is our last class of the semester, corresponding to what is it? Wednesday the 15th, right? I'm taping it early. I would like to post it early so you guys will have extra time to look at it. As I promised, I am going to dedicate this lecture. I have put a tremendous number of hours trying to digest things and make it as simple as I can and as summarized as I can, because it is a very important topic and I felt that we sort of rushed through it somehow. It just didn't work out right. The issue of stress strains and their transformations. So I will present it, I will show you some examples and so on. I will prepare a package of practice that will be posted with solutions as we've done already with regards to some other parts. I guess this will be package number 2. There's already one for indeterminate structures and virtual work or something. Then this will be 2 for the stress strain, and then there will be something else for the first part, which was the calculation of stresses on beams of arbitrary cross sections and so on. Okay, now let me just say from the outset that I do not intend to give you questions in the final that are intricate questions about the subject that we're discussing now. I can ask you something fundamental, but I will not ask you something that is particularly difficult. However, I am presenting the material to you because it is important from a professional point of view that you have these ideas as clear as it's possible at this level of your engineering education. Okay? So let me begin by saying that we are going, of course, this should not be as difficult as hearing it for the first time. Well, I don't know if difficult is the right word, but anyway, it should be easier because we've already went through it. 85% of what I'm going to say today, or maybe 80% or something, we've said before in one way or another. But now it's going to be more organized and complete, right? So don't take a position when you listen to this as if, just thinking in terms of exams or evaluation. Try to take a position of, okay, here is a lecture about stress strain. This is what you got from your undergraduate class in structural analysis. So first, let's just say that if we plot stress versus strain in a very simple unidimensional situation, right, where we take a bar and we pull it with a force F, and the bar is of length L, and the bar gets longer by an amount delta, then in the simplest of manners, right, this uniaxial strain is just the elongation divided by the length, and the stress would be the force divided by the area, right? Now, if we were to plot the stress versus the elongation, depending on the material, it might be linear for a while. This is what we refer to as elastic, right? But if we make the stress large enough, then all materials will eventually, unless they're completely brittle and just fracture, but they will eventually deviate from that straight line, right? And so all materials are eventually nonlinear, or they are just perfectly linear and then they fracture, let's say glass or something like that, right? So this is nonlinearity, right? We are in this class, when we deal with these relationships between stress and strain, we are restricting ourselves to the elastic, actually I shouldn't say elastic, to the linear part of the diagram. I was going to use the word that I was going to say don't use because this part is linear, right? It's a straight line relationship. The term elastic, to be precise, means that if you load and unload, you use the same path. So for example, if we were to load along this path, let's say stress and strain, and then you unload, and as you unload you come back on the same line, right? Then we can say that this is elastic, even though it is not linear, right? So something that is non-linear can be elastic, right? We are going to be, when we talk about stress-strain relationships, we're going to be restricting ourselves to the part of the load deformation curve which is elastic and linear, right? In fact, in the case where it's linear, it's basically elastic by definition, right? It just comes back on the same path. So, okay. Now, as we discussed in class, stress is a tensor, meaning that it is not a scalar. You cannot say the stress is 5 and be precise. You cannot say the stress is with 2 numbers. In the general case, the stress is the values that we looked quite a bit on that cube, right? That 3D cube. That it's like this, right? And in that cube, let me try this new colors here, see if they work. In this cube, we can say that we have the positive x phase, right? And in the positive x phase, we have sigma x, right? And then in the back there is the negative sigma x. And then in the positive x phase we have a shear stress this way, which is tau x in the y direction. And then we have a shear stress this way, which in this case would be tau in the x phase in the z direction, right? Likewise, if we go to the positive y phase, we have a stress sigma y, and then in that positive y phase, this shear stress this way would be tau in the y phase in the z direction, and this shear stress here like this would be tau in the y phase in the x direction, right? And of course those ones exist down here also. And then we finally have the z phase, where this is sigma z, and then this would be the shear stress in the z phase in the y direction, and this is the shear stress in the z phase in the x direction, right? Now, when we put those 9 numbers together, we can refer to it as being the stress tensor. And so the stress tensor is a 3x3 matrix that contains 9 numbers, right? That stress tensor is sigma equal, let's put it with a bar on top so we know it's the tensor. That would be sigma x tau xy tau xz, and it is symmetrical. So this is tau yx and tau zx. This is sigma y and this is tau yz. That's tau zy, and then this is sigma z. So the stress tensor is symmetrical and has that form. Okay? The strain has a tensor which is in all form equivalent to this one. And when we refer to it, we would say that the strain tensor is another matrix corresponding to sigma x. There would be a strain in x. Corresponding to the shear tau xy, there would be a shear strain xy. Corresponding to the tau xz, there is a shear strain xz, and this one is also symmetrical. Then there is epsilon y and gamma yz, and then there is epsilon c. And this is the strain tensor, right? So we have, if we write it in tensor form, which is as a matrix, this is the strain tensor, that's the stress tensor. Sometimes, a little bit later, soon, we will find it convenient to write sigma as just a vector of the independent values. So we may also refer to sigma as being sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. So this is also the same thing, it's just this stuff ordered like that, right? Likewise, we can refer to the strains also as a vector for convenience, sometimes as ex, ey, or epsilon x, epsilon y, epsilon c, gamma xy, gamma xz, and gamma yz. Right? So this is the general situation. Now, the first thing that we learned, eventually we will get to Mohr circle as a refresher, but one thing that we want to, well, not that we want, that you can think it's obviously important, right, is that the reality of the stress at a point, or of the strains at a point, will depend on the orientation of the axis, right? So if you were, I'm just trying these different colors, so if you were to take, I don't know, some other axis, right? Imagine three things perpendicular and you just kind of go like this, right? Put it in some sort of arbitrary position. This is a point which we show with dimensions, but the same reality that we have here, if we express the numbers over here, we will get different numbers, right? It is the same reality, but the point of view is changed, right? So the question then is, one of the things that it is of interest in engineering is being able to take the stress at a point, which is described by the stress tensor, right, and examine how that changes if we look at it from different angles. So if we rotate the reference system, how does it look, right? Because this is of interest for a number of things. Now, we will not do, we have not done in we did not do in class, and we will not do in exam or in practice these general rotations, but I just, for your general education, I just point out that the way that you go from x, y, z to x prime, y prime, z prime involves three angles, and those angles are called the Euler angles, okay? So to go from x, y, z to x prime, y prime, z prime, the way to view it is that you do it with 3 rotations, right? And these 3 rotations are called Euler's angles. So the Euler's angles pass you from xyz to x prime, y prime, z prime. I will not describe them. You can actually, I had them here, but I figured now that I'm doing it that it may not be that important. So the point is, actually I noticed that I drew this a little bit different than I intended to, because I wanted to show the parallelism a little bit more clear. So I had the y kind of going up, so maybe I should have had this one as being like y prime, and then maybe this one being z prime. Not that it matters, but, and this being x prime or something like that, right? So, took the set and just went like that. Okay? So, there are some angles that are called Euler's angles and are the 3 rotations that you can go from here to here. Once you know those rotations, there is a transformation matrix that allows you to compute the stresses in the new set without any difficulty. Okay? So the stresses in the stress tensor in the newly oriented system, for example, if you have the stress tensor sigma bar, right, and you want to get the sigma bar prime, then it turns out that the sigma bar prime, which is the new system, this, let's say this is in x, y, z, and this is in x prime, y prime, z prime, right? So how are they related? It's just a matrix times sigma bar times the transpose of that matrix. And that matrix A, okay, can be written as a triple product, which I guess I'll just write it for once for you so you see it. So this is cosine of phi, sine of phi, 0, 0, 1, minus sine of phi, cosine of phi, 0, 0. Times, that's the effect of the first rotation. Then the second rotation is 1, 0, 0, 0, 0, cosine of theta minus sine of theta minus sine of theta cosine of theta. That's the second rotation. And then the final rotation that gets you to where you want to be is cosine of phi, sine of phi, 0, 0, 1, 0, 0, minus sine of phi, cosine of phi. So it's a tedious multiplication, but it's no big deal once you program it, right? So given phi, theta, and see here, you evaluate these 3 little matrices, multiply them together, and that is your matrix A, which pre-multiplying your tensor and post-multiplying times the transpose gives you the new coordinate system. Now, okay, so that's just so that you've seen it once, right? So what do we actually do in class? Or what are we most interested, let's say, as an introduction, because it covers a large class of practical problems. We are interested on the special case where instead of dealing with the stress tensor in general, we reduce the tensor to the case of two-dimensional analysis, right? So in 2D, right? In 2D, we are only dealing with sigma x, sigma y, and one shear stress, which I'll call it tau xy, okay? So in 2D, the cube gets shrunk. We are just keeping the XY plane and saying that's the plane of our two-dimensional analysis. We are now interested still on knowing if we have an element in XY, right, that has some sigma x and some tau. Now, if I'm going to present it with more circle, I should have it like this, because that's what we did for sign convention positive, right? And sigma y. So if we have a stress element that is described in xy this way, we may want to know how would that same reality look if we decided to look at it in an inclined direction, x prime, y prime, right? And the translation between the reality viewed in xy to the reality viewed in x prime, y prime is of course a particular case of the previous general 3D, right? In which only one angle had to be used of the whole three things. And we could arrive at the Mohr circle by making the second two angles 0, doing all kinds of stuff, right? But the bottom line is that the equations that connect the orientation, any orientation, to a new one that has been rotated by some angle, we learned in class, and this one I just repeat very quickly. We learned before and we said, okay, if you want to know what is happening in the new orientation, you can use Mohr circle. And Mohr circle consists on plotting on the horizontal axis the normal stresses and on the vertical axis the shear stress, where we agreed for geometrical reasons to take that kind of shear stresses as positive. That is, the shear stresses that produce clockwise rotation of the element are plus. So if we had an element like this, we would say, okay, so sigma x is here, and that is occurring with a positive shear stress equal to tau, and then the negative, the y phase is, let's say, here, and it's always with the opposite direction of the shear, and then the points get connected. This is the center of the Mohr circle, and then we just simply draw the circle, and we realize that we know that all the points in the circle, right, correspond to inclinations here, except that the angles on the circle are twice the angles in reality. So this would be the x phase, right? So if we wanted to rotate, if this angle was, I don't know, 20 degrees, we would, and that's a counterclockwise rotation from the x phase, then we would go 40 degrees here, right? And we would say, okay, go 40 degrees from the x phase. What happens here, that is your x prime phase, right? All right, so this we've done, and I conclude this very brief going over by just simply reminding you, or not reminding you, noting, right, that this Mohr circle in 2D is just a codifying of the equations that apply in the general rotation of the stress tensor in 3D to the case where we are only interested about rotating with respect to one axis, and there are only stresses in 2D. So that's why we're only rotating about one axis. And then instead of looking at what the equations are, we realize that those equations can be coded into a procedure that we know as Mohr circle, and which allows us to do this thing very quickly, okay, and very easily. So, let's see. As a final note of refreshment, or refreshing your memory, not refreshment, remember that in Mohr circle, right, when we plot sigma and tau, and another sigma and another tau, and we go like this, and we have our circle, right? So these values here are called the principal stresses, right? And those are the directions of the principal stresses. So this is principal maximum, this is principal minimum, and we also have, right, well, it's kind of not correctly curved, but we also have tau max, right, which is the maximum shear stress. All right? Notice that the drawing of the maximum shear stress is always going to be 90 in the circle from the principal, and therefore 45 degrees in reality, right? Okay, so so much for the Mohr circle and the rotation of the stress tensor. Now the part that we really did much more poorly, I think, was elasticity. So now I took the time to summarize it well here. You should make notes to yourself of the equations that will appear here, okay? In case that you have to use them in the exam, you have them handy. Which, by the way, when the exam comes this time around, the final, we're just going to say, like I didn't say anything with the midterm, so we'll treat it as being open book, open notes. So you can just look. I do not recommend that you rely on this fact, because then, you know, time is limited. You can't be just trying to figure out where everything is. Let me see if I can find this and that. I would still suggest you make a couple of summary sheets, 2 or 3 or something, and put all the stuff. And okay, so let's look at elasticity. By what we mean by elasticity is we want to see the relationship between the stresses and the strains, right? Stresses come in, they produce strains. Strains, when they get integrated over the complete body, they are the ones that produce the deformations that we've now been computing using virtual work for a while, right? So in this case, it's convenient to write sigma, as I said, as a vector. In this case is 6 by 1. There is this matrix 6 by 6, and then there is the strains, which would be a 6 by 1, right? This we looked in class. We noted that because the matrix S is symmetric, that means that only half of them are independent. So it would be 6 plus 1 is equal to 7. So it's 21 constants in general needed to fill this matrix. But if the material is isotropic, which is the typical assumption that often is assumed to hold, then all these 22 constants become just 2, and we normally choose for these 2 Poisson's ratio and Young's modulus, or the modulus of elasticity. Now, for isotropic materials, what is the relationship between stress and strain? What is the relationship between stress and strain for isotropic materials? So here it is in general. You know, the stuff that you just say epsilon is equal to, sigma is equal to E times epsilon. Well, this is the real thing, right? Now, sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz, right? Those are all the stresses. And how are they related to the strains? Well, they're related to the strains like this. E, 1 plus nu, 1 minus 2 nu. And then here comes the 6 by 6. That multiplies the associated strains, which are epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma xz, and gamma yz. Now this matrix 6 by 6 looks big, but it's very easy, because if you partition it into blocks of 3 by 3, this is 0, and this is 0. And then this one here is diagonal, and it's just, actually let me just write it like this, A, where A is equal to 1 minus 2 nu over 2. Okay, try just to write less. And this one here is just 1 minus nu, I'm sorry, 1 minus nu, 1 minus nu, 1 minus nu in the diagonal, right? And then in the off diagonal is just nu, and it's symmetric. So you see, it's kind of, even though it's big, it's really very simple to write, right? This, everything not shown in this block is zeros, and this is just symmetrical in its own 3 by 3, right? This is 3 by 3, 3 by 3, right? So you have two blocks of 3 by 3s that are 0. The corner here is just 1 minus nu in the diagonal and nu in the off diagonal, and the bottom one is just a diagonal matrix A, you know, with the same entry every time, where the entry is 1 minus 2 nu over 2. So that is the relationship where we've left temperature out, just for simplicity, because we're not going to do problems with temperature. But that's the relationship between stresses. Whoops, why did I erase that? That's the relationship between, so A is equal to 1 minus 2 nu over 2, right? So this is the relationship between the stresses and the strains in general. Now, you can also flip that around, right? And write what are the strains. So epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, and gamma yz. So the question is, how does the strains relate to the stresses? Well, it's just the inverse of the matrix. But it turns out that the inverse in this case is just 1 over E, and the matrix is like this. Once again, you get something that is partitioned into 3 by 3 with zeros on the off, right? You also get a part here which is diagonal, and you can call it B, 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 where B is equal to 2, 1 plus nu. Okay? And on this side, this one it may be even easier, is just 1, 1, 1 in the diagonal, and in the off diagonal is just minus nu, and it's symmetric. Oops, should get myself room here to write that. Of course, this is multiplying sigma x, sigma y, sigma z, epsilon, I'm sorry, not epsilon, tau xy, tau xz, tau yz. And B was 2, 1 plus nu. Okay, so you have there in front of you the relationship between stresses and strains, or strains and stresses, in the case of a linear isotropic material. It is only a function of two constants, E and Poisson's ratio. All the formulas that are simplifications that we will be describing in the next few minutes are coming from here, right? So we can take and say, in some instances we don't have to deal with the full 3D. We might, just like we did with Mohr circle for rotating stresses in the plane, we might be interested in just simply relating stresses to strains in the plane, right? Not in 3D. All of those things that are coming, there will just be simplifications from here. I will not be able to have them simultaneously as I present the equations to you, but you can easily confirm yourself that the results I'm going to give you follow directly from there. the two cases that we are interested in, I can actually put here without, without having to erase. The A and the B are no longer necessary here, you know what they are. But I can write this here. One case that we are interested in is what we call plane stress. Now you might think, what do you mean plane stress? Although we discussed it in class, but what do you mean? If we're going to go to plane, why is it not always plane stress? No. If we go to plane stress, what we are saying is that these are the assumptions. There is no stress in the z direction, and there is no tau xz, and there is no tau yz. So that's what we mean by plane stress. So if we want to know what is plane stress, we would come to this statement here, and notice that sigma z is 0, tau xz is 0, tau yz is 0, and we would see what we get over there. Okay? Then we would go with those over here and see what we get over there, and so on. But this is what defines plane stress. Now, we also are going to be interested in looking at plane strain. The case of plane strain differs from plane stress in that what we assume is that epsilon z is 0, and then corresponding to this we got gamma xz equals to gamma yz is equal to 0. Again, if you take, in both cases, notice that plane stress and plane strain, okay, are not like this or this. Both of these two things here are the same relationship. This is just something connecting stresses to strains, and this is just the flipped version, strains to stresses. In both cases, when we want to see what happens to plane stress, we actually put it here and see what both things, how they simplify. When we want to see plane strain, we put these assumptions here and we see how it simplifies. Okay? And when you do that, you get the following results. Okay, so this is what happens after that replacement is done. In plane stress, you can check this stuff, might be in your notes exactly the same from before, but as I said, I thought we kind of didn't hammer it enough. So in plane stress we get this. Instead of having to write 6 things, we have this relationship. Okay, multiply times epsilon x, epsilon y, and gamma xy. So that is the relationship between what? Stresses and strains in plane stress. When we take the inverse, there is a detail here, because you will see that in the inverse I will have ex, ey, but I will also have EZ, because it turns out that in plane stress we don't have plane strain. So when we do the substitutions on the previous general case, I get 4 when I look at the strains, not 3. Notice that this here is not the inverse of this one directly, because then I wouldn't have EZ, right? I'm going back to what I just erased, plugging in the assumptions of plane stress, and then seeing what the two relationships give. And what we find is that the first relationship gives this, and the second relationship gives 1 over E, and now we have 4 columns. It's 1, 1 minus nu, and 0, minus nu, 1 and 0, minus nu, and 0, 0, 0, and 2, 1 plus nu. close this, and then this is times sigma x, sigma y, and tau xy. Okay, so there you have it in clean. The generic relationships that I just took out, that you have before, which were both 6 by 6, right? When they get simplified to the case of plane stress, and plane stress was defined as what? Plane stress is defined as sigma z is equal to 0, gamma xz equals, I'm sorry, not gamma, talking stress, tau xz and tau yz equal to 0. So if we put those assumptions on the general 6 by 6, both of the two 6 by 6s, we get this on the first one, this on the second one. So if you are dealing with any problem in which the problem is plane stress, then you're dealing with these relations. Any answer to any of those problems has to come from these two relations. Okay? So that's plane stress. Now, the next one is plane strain. So, plane strain, if we take our relationships of the 6 by 6 and we bring them in and we translate, plane strain is what? Plane strain is epsilon z is equal to 0, right? And so is gamma xz and gamma yz are 0. We take that to our generic expressions, substitute, simplify, and we get the following. Epsilon x, epsilon y, and gamma xy is equal to 1 over e times 1 minus nu, 0, minus nu, 1 minus nu, 0, 0, 0, 0, 2, 1 plus nu, close, and that's multiplying sigma x, sigma y, sigma z, and tau xy. Because what? In plane strain, we are not saying that there is no stress in z. There is a stress in z, right? And this is what we find. We have plane strain, so these are the only strains. Ex, Ey, gamma xy, this is how they're related to the stresses. And the inverse relation, not going back to the original, is that these guys, sigma x, sigma y, sigma z, and tau xy, are given by E divided by 1 plus nu, 1 minus 2 nu, and then we have 4 rows, 1 minus nu, nu and 0, nu, 1 minus nu and 0, nu, nu and 0, 0, 0, and 1 minus 2 nu divided by 2. That gets multiplied times, as you might expect, these guys, right? Which are epsilon x, epsilon y, and gamma xy. This is plane strain. So, what do we have? We have, not all there on the board at the same time, but what we have is 6 by 6 relations between the general case of stresses and strains, or the flipped version, strains and stresses. That's general. Now, what are the two simplifications that we often handle in practice? We can say, okay, we'll have all our stresses in one plane. That's plane stress. How do these 6 by 6s simplify? They simplify as to what I showed and erased now. The other possibility is we may have plane strain. What if we have plane strain? Well, if we have plane strain, then those 6 by 6s simplify to this case here. Okay? Now, as a little bit of a commentary regarding when you have plane stress and when you have plane strain in physical sense. If we had, let's see, if we have a cantilever beam, let's say like this, let's say fixed here, doesn't matter. The point is that this dimension is T, this dimension is H, this dimension is L, right? We apply some loads to this thing. If we look at an element of stress here, this is a point on the beam, right? We would normally refer to this as plane stress. Why do we refer to that as plane stress? Because if you think about this being the x-axis and this being the y-axis, and let's say the z-axis is coming out of this board, right, towards you. There are no significant stresses in z here. Why? Because the two z faces are very close to each other, right? The positive c face, well, not positive, but let's say there is a c face that is the one that our eyes would see if I see the beam here, and there is another z face that is just t behind it, right? So within that depth, there cannot be much going on, right? So this is basically a plane stress situation in which our stress elements would have, you know, at best things like this, right? There's nothing going on in the z direction. Now, so the typical thin beam plates and so on would be plane stress. Now, if we had this beam was very thick, I'm using the same example to make the point. But now let's say that from here to here, you know, it's a lot. It's, you know, 2 feet or something like that. Not a few inches, you know, and this is 10 feet or something, you know, and this is 4 feet. Now, if the x-axis was coming out this way and the y-axis was going that way and the z is coming towards us, this z face and the other z face are far apart, right? They're 2 feet apart. So if you imagine a cut along the center of this thing, and you see that plane, the plane that it's cutting through the middle, a stress element in the middle of that plane cannot grow in the z direction because there's a lot of material on both sides. So in that case, we would tend to call this plane strain, at least in the near central region of this. Of course, if we get to the edge near the z face, then of course we're back to plane stress because there is no z stress here. But if we were in the middle of this thick thing and we wanted to study the stresses in the middle of this big chunk and we took a cut, then we would say that we would probably be best showing something like this, right? But realizing that in the z direction, we should not say that sigma z is 0. We should say that epsilon c is 0, right? So really, what determines plane stress or plane strain is which one of the two assumptions, sigma z is equal to 0 or epsilon z is equal to 0. If sigma c is equal to 0 is the logical one, then you're in plane stress. If epsilon z is equal to 0 is the logical one, then you are in plane strain. In practice, it's seldom any situation that is perfectly plane stress or perfectly plane strain. They're just idealizations that allow us to handle certain things faster, or not faster, with simpler equations, right? Okay, so you have all the equations needed for elasticity in the linear case and their simplifications to plane stress and plane strain. Let me see. Actually, I made a little summary here, which is a little bit redundant, but I'm going to put it in because I kind of said it already. But I put something like this: plane stress, plane strain. If you have plane stress, you have sigma z equals tau xz equals tau yz equals 0. Right? And then from here, you can then say that the strain field is epsilon x, epsilon y, epsilon z, and gamma xy. So these are the deformations, right? So you're in plane stress, those are the zero stresses, these are the non-zero strains. If you are in plane strain, then in plane strain, what you have is epsilon z and gamma xz and gamma yz is 0, right? And the stress field of non-zero is sigma x, sigma y, sigma z, and tau xy. These are non-zero stresses. Okay. Okay, so a couple of two little things and we're almost done with that review. What is this one? There is something that you should at least see it once real quick. It's actually extremely simple. It has to do with volume change. That is, when a structure is loaded, before it's loaded it has a certain volume, right? When you load it, there are strains. Some things get longer, some things get shorter, and so on. And a question that comes to mind is what happened to the volume? Did it get, do we have more volume, less volume? What's the deal? So for that, you can think this way. Imagine that you have something that is Lx by Ly by Lz, right? Some sort of a cube. The volume of that cube is obviously Lx times Ly times Lz, right? That's the volume. Now, if that volume, and you can think about Lx, Ly, and Lz as being, if you like, very small, so that the strain is constant with it. This analysis is done under the premise of constant strains. But once this system gets loaded, we are saying that the dimensions now after loading would be, Ly times 1 plus epsilon y, right? Why am I doing this? This one would be Lx times 1 plus epsilon x, and this one would be LZ times 1 plus epsilon Z. So this is before loading, and this is after. So the dimensions change by the strain in that direction. In other words, that length is the original length, Lx, plus the increasing length, which is Lx times epsilon x. This dimension is Ly, plus the increase in that dimension, which is Ly times epsilon y. This dimension is Lz, plus the increase in that dimension, which is Lz times epsilon z. So it's a very trivial thing, right? What is the volume of this? As we said, is Lx times Ly times Lz. What is the volume of this? Is Lx times 1 plus epsilon x times Ly times 1 plus epsilon y times Lz times 1 plus epsilon z. Right? Now, if you multiply all that and subtract this and neglect higher order terms, what you find is that delta, okay, this is B0 and this is B1, let's say. This is the 0, this is the 1. So if we take the volume 1 minus the volume 0, that's the change in the volume, right? And what you find after you do all the multiplications is that the change in the volume due to the strains is equal to the original volume multiplied times Ex plus Ey plus Ez. Of course, that's neglecting higher order terms, but that's it. So this is just a formula that I wanted you to be aware of that says the change in the volume is equal to that. Now, why is it interesting? Well, it's interesting on a number of things, but let's take a look at the implication of that equation in the case where the stresses, well, let's see, how did I do it? If you go back and you look at the general case, you would find, go to general epsilon equals something sigma, right? Where this is 6 by 6. So looking at that expression, you will find that epsilon x is equal to 1 over E sigma x minus nu sigma y minus nu sigma z, right? And likewise, there will be an expression for epsilon y, and likewise, there is an expression for epsilon z, right? Now, consider the case where sigma x is equal to sigma y is equal to sigma z. That is, assume an isotropic state of stress, or a uniform state of stress all over, right? In this particular case, then you can see that epsilon here, right? This epsilon, which is equal to any one of them, epsilon x would be equal to epsilon y, would be equal to epsilon z, and would be equal to what? To 1 over E, sigma is common factor, right? Of what? Of 1 minus 2 nu, right? So this would all be the same, and if we substitute here, we would find that in that particular case, the change in the volume is the volume times 3 times this, right? Which would be 3 times sigma over E times 1 minus 2 nu, right? Well, what is interesting about that? There's one thing that is interesting, which is as follows. If that's the change in the volume, wait a minute. Did I do that right? Hold it a second. Let me stop it and start again just to shorten this thing.